Now in this next video, we're going to continue our discussion of function behavior, but I just realized, having talked to a few other students, that some of us may not have seen function behavior written this way. In this particular example, this is from Chapter 3, Section 2, number 35. In this example, we have two functions. We have f of x, which is red on the screen, and g of x, which is blue on the screen. And those two functions are independent of one another. They're not affected by each other. But we're actually being asked to evaluate what would happen if we evaluated a value within a combination of those functions. And this may be new to some of you, that we can actually add together function results or functions in their entirety, as well as evaluate them at a particular target simultaneously. And that's exactly what's happening here in question A. In question A, actually let me put that right here. In question A, we're being asked to evaluate the function f plus g evaluated at 2. Now that notation may trip some of you up, but in a sense, we can kind of think of this as a distribution. I don't want you to get really hung up on that, but what this is really asking us to do is evaluate the function of f at 2 and the function g at 2 and add the two results together. Now, if I knew the actual equation that represented g of x in this case, and if I knew the equation that represented f of x, I could add those two functions together and evaluate that result at 2, and that would give us the same thing. But in this case, since we don't know the actual equation that creates f and g, then we're going to go about this way. By the way, I mean, this is a quadratic equation and this is a linear equation. I'd be willing to bet that you could figure this one out. You could probably find the equations of both of those. But f evaluated at 2, well, that's this key data point. I'm looking at 2 on the x-axis, and I'm looking at the y result for that function. And then g evaluated at 2 is this position right here. So again, I'm looking at 2 on the x-axis and determining the y value at that. F of 2 ended up equaling 2. G of 2 ended up equaling 1. So f plus g evaluated at 2, I would argue, is equal to 3. And similarly, we can answer the remaining questions. F minus g evaluated at 6 is really the same as f of 6 minus g of 6. So f evaluated at 6 is 0, and g evaluated at 6 is 1. So I like -1 as the result here. Go ahead and pause the video now and try the remaining problems on your own. Resume playback in a moment to check your work. Okay, and I realized that I had question B and C reversed, or I answered what I thought was B, and that was actually C. So these are the results that I would have gotten. For question B, the answer I ended up with was -2. For C, I got -1, and D, I got +1. You may have noticed that C and D, the equations look quite similar to one another, but the order does matter when subtracting. Subtraction is not a commutative operation, so we do have to be aware that we must subtract in order to obtain the proper results. For question E and F, we had a product of two functions evaluated at 2 and the quotient of two functions evaluated at 4. But here again, all of these operations perform as you might expect. We can actually evaluate the combination of these functions one at a time and combine their results. Now this is different then, so let's make a note here. Combinations of functions, that would be our add, subtract, multiply, and divide that we saw here. Combinations are not the same as compositions. So you may have seen or heard of a composition of functions. And these are, it's a completely different operation when you compose two functions. So combinations are not the same as compositions. With compositions, we use a symbol that looks really similar to this multiplication notation, but it's an open circle and not a closed dot. F composed with G at some value or at a letter X. And with this, we actually take an entire function and substitute it as a variable inside of the outer function. We sometimes write it this way, F composed with G at X, where we use nested parentheses notation, and we actually fill, again, functions within other functions. We're going to spend some time talking about that at another time, at a later date in a different section. But for this particular unit, we're just worried about the combinations: add, subtract, multiply, and divide. Now, another skill that's important to have when we operate in higher level mathematics is to kind of predict the behavior of functions before we actually graph them, or before we even see an equation. We sometimes want to know what the behavior of that function is going to be. And so we have to internalize or make an educated guess as to what the graph of a particular function might look like. So in this particular example, we have 5 descriptions and 5 graphs to look at. And what I'd like for you to do is read these 5 descriptions and try to match the graph that's associated with each of these descriptions. So take a couple moments here, read the descriptions, and try matching each graph to those descriptions. And these are the results that I would expect for you to settle on after thinking about this a little while. Graph number 1, I think, matches description E, the height of the golf ball hit with a 7-iron as a function of time. And you don't have to be a golfer to really know the specifics here, but essentially at time 0, the golf ball should be on the ground, and at some time in the future, the golf ball will be on the ground again. And in between, the golf ball will rise in height, and then eventually will fall in height due to gravity. So we would expect to see a function increase for a certain amount of time, and then that function value would decrease after a certain amount of time. Graph number 2, I think, matches A, the temperature of a bowl of soup, as a function of time. One thing you may or may not be aware of is that a hot object, when placed in a room to cool, will lose temperature very rapidly. So the steepness of this curve at the beginning is relatively steep compared to the steepness along the curve as time passes. This gets less and less steep. And it's not entirely clear in this particular diagram, but this curve will actually level off towards the ambient air temperature, the temperature within the room. So it's not real clear with the diagram here, but it is actually leveling off and getting closer and closer to this particular target value. It doesn't necessarily reduce to 0. Now, question 3, I think, matches description D, the distance traveled by a car going at a constant velocity as a function of time. Some of you may have been thinking, well, constant velocity, doesn't that mean that the graph should be perfectly flat? And, well, if we were graphing velocity, I would agree with you. A constant velocity would be flat if the y-axis was velocity. But in this case, the distance is what we're trying to graph. So that's our y-axis here. If we're traveling at a constant rate of speed, that means that our total distance is increasing as time passes, and it's increasing at a constant rate. In other words, the slope or the steepness of this particular graph has to remain consistent. It's not like A, where the steepness varied over time. In this case, the steepness remained very consistent, and our graph ended up being a nice straight line. Question C, I would argue, is the population of Texas over time. And again, you don't have to be a scholar with regards to population of Texas in this case, but populations in general in most locations increase somewhat slowly at first, and then as more and more people increase the population, then the rate of population growth tends to grow faster and faster. So in this case, I would expect to see this essentially an exponential growth function for question C, or part C. And then for part B, this one may be a little bit hard to interpret at first, but the number of daylight, or number of hours of daylight per day over a 2-year period. Well, if you think about what's happening during the change of seasons, during the summer months we have lots of daylight, and during the winter months we have much less. And then summer, winter, summer, and so on and in between. So the number of hours of daylight tend to oscillate between a maximum and a minimum value. And if you were unaware, those values remain pretty consistent over time. The amount of daylight that a particular area sees in the summer is consistent from year to year, and so we would expect to see this oscillating pattern. That would be good to know if we were being tasked with finding the equation of that pattern, and that's actually a really good exercise for our trigonometry class when you find yourself taking that course. Now, in the interest of time, I am going to skip these 3 examples, identifying absolute and relative maxima and minima. We actually did these in class last week, so you can refer to those notes. And then also same thing with average rate of change. I think I'm going to skip that problem because, again, we've had enough practice with average rate of change. So the last thing that I'd like to do is spend a little bit of time with our graphing calculators, not Desmos, but our actual graphing calculators, and use the graphing utility to approximate local maxima and minima. And I also like to show you how to adjust the window size on your calculator, as well as the accuracy of your calculator when it displays decimal results. So on the calculator, I'm just going to create a new page, just like we usually do, pressing the on button, choosing option 1 for a new document, and we'll say no, we don't want to save that last document. Whoops. Said no, we don't want to save. There we go. So I'm going to create a graphs page right off the bat. And in the function bar, I would like to enter this function, 6x cubed minus 12x plus 5. So 6x to the 3rd power minus 12x plus 5. Let me double check that. So 6x cubed minus 12x plus 5. Now, what's interesting here is that we're told right off the bat what domain we want to focus on this function. So we're only going to focus on x values between -2 and +2. And that allows me to adjust my window pretty quickly. I'm not interested in every single x value in this graph. Instead, I'm going to jump into the menu, choose option 4, and then select number 1 to adjust the window settings. We're going to specify the x minimum to be -2 and the x maximum to be +2, and I'm just going to press enter. We can see most of the graph here, but we can't see the whole thing, so I'm going to jump into the menu one more time, choose option 4, and then option A. This will adjust the y-axis to fit the x-axis that we just established. So there we go. There's the behavior of the function within the window that we're interested in. And so the question then goes on to ask, approximate where f has a local maximum and where f has a local minimum. Now, I don't recall for certain if this is going to come out to be a decimal answer or not, but when I ask a question like this on our test, rather than estimating by simply looking at a graph and calling it a day, what we mean here is to actually use the calculator's utility to find the local maximum and minimum, and we want to show accuracy to about 4 decimal places. Accuracy to 4 decimal points. So let's see if we can do that with our graph here, and let's see if we end up getting decimals as a result anyway. So our maximum point will occur somewhere around here, and our minimum point down here. We can find both of those by using the menu, option 6, number 2 for minimum. Then we'll choose menu, option 6, number 3 for maximum. We've done this a couple times in class, so I'm going through that kind of quickly here. If you have specific questions on how to do that, please make sure that you send me a message or ask me when we see each other in class. As of right now, we've got some pretty decent results, and they are estimates for our location, but I do want some more accuracy than what's shown here. So we can fix that. If we go into the menu and choose the settings this time, we haven't done this before, but we'll go into the settings. The display digits is what we'll adjust here. Now, float 3 says that it's going to show essentially 3 significant digits, sometimes to the left of the decimal, sometimes to the right. But what I would like to do is try this auto option. Actually, no, I tell you what. Let's try the float option. I think that's going to be better here. This will show as many decimals that'll fit on the screen for the graph with which we're working. And so there we go. Float was pretty good for this decimal. It wasn't too good for this one. It didn't actually give us the 4 decimal places, but the other ones were okay. So sometimes that float option works just fine for us. We could round to the 4th decimal place from here as needed. But I'm going to jump into the menu and choose the settings one more time. And let's see what happens if we scroll down just a little bit more to the bottom to where the fix options are. We can choose fix 4 and press OK. Now what this will do is it will force the calculator to display 4 decimal places to the right of our decimal point, and it'll perform any rounding as needed. So in this case, we can very clearly see that the x values, one's a positive 0.8165 and the other is a negative 0.8165. And then we've got the 2 y values associated with it, all of which have been rounded to the 4th decimal place. And there we have it, a maximum point and a minimum point identified. Now, with those points identified, we can then talk about the domain on which the function is increasing and where it's decreasing. Because here again, we recognize that a maximum point occurs from when the function is increasing and changes to a decreasing function. And then again, a minimum point occurs when the function changes from a decreasing function to an increasing one. So essentially between this point and this point, considering the x values only, that's where our graph is decreasing. And if we go to the left of this data point and to the right of this data point, that's where our function is increasing. So we might say something like this. The function is increasing when the x values exist between negative infinity up to negative 0.8165, and then again from 0.8165 positive to infinity. And our function was decreasing for all x values that exist between negative 0.8165 and positive 0.8165. And here's a nice way again to illustrate or demonstrate the x values or the domains on which the function is increasing or decreasing. And we can do so, we can answer those questions very quickly by locating our maximum and our minimum points, because those x value positions are what determine the change in increasing and decreasing behavior. So I hope that video helps. I know the second one got to be a little bit lengthy, but I think the conversation points are worthwhile. Thanks for watching, and I'll see you probably tomorrow in class.